Hello and good morning. In this video, we are going to study topic number 3, which is beam area or beam solid angle. In the last lecture, we discussed pattern of an antenna. A pattern of an antenna consisting of major lobes and minor lobes requires measurement of area of those lobes, which is called as beam area. However, the beam area of an antenna cannot be measured using a conventional method of angles, and therefore we need to go back and learn a concept from physics, which is plane angle and solid angle. Let's have a quick look at these two concepts. A plane angle is measured in radians, whereas a solid angle is measured in steradians. Let's first understand quickly what is a plane angle. From a point when there are two lines making angle theta, they cover an arc of length r. So this angle theta can be measured in radians, and if we extend this arc to form a two-dimensional structure, which is a circle, then the circumference of the circle is given by 2 pi r, and the angle theta is given by the circumference divided by the radius. In this case, we consider the radius equal to r. So 2 pi radians is the total angle subtended in a full circle. So this is a one-dimensional measure for a two-dimensional diagram. Now when we come to solid angle, which is measured in steradians, steradian is a measure very similar to plane angle, but the measurement of solid angle is done with the area of a particular structure that we are considering in 3D view. The circle in 3 dimensions becomes a sphere. So we can show a circle as a sphere, and the angle measured is given as ratio of area to the square of radius. So if we consider this as a radius, very similar to this case, then it is not arc subtended, but it is the area subtended. So this way, here this particular region is called as a solid angle. So if we are taking example of a sphere, because the radiation pattern of an antenna is a sphere. It is an isotropic radiator case, which is a very special case, a fictitious antenna which practically do not exist, but it produces a radiation pattern of sphere because it equally radiates in all directions. So for a sphere, the area is 4 pi r square divided by r square, that is square of the radius, is equal to 4 pi steradian. 4 pi steradian is the solid angle subtended by a sphere. Now, next, in order to understand the concept of solid angle, we need to understand this diagram representing polar coordinates showing incremental solid angle dA. This is an incremental solid angle. It's a small area covered on the surface of a sphere having a radius r. So since this entire diagram is drawn at once, there is a little confusion about how the diagram is developed. Once we understand the development of this diagram, we can easily understand the area dA, which is an incremental area. So let us develop this diagram by considering 3 axes, namely Z, X and Y. Z axis represents theta equal to 0, which is polar angle, x represents phi is equal to 0, which is azimuth angle, and since it is a polar coordinate system, we need to represent the variation in angle phi and theta. So first let's represent the variation in angle phi by considering this arc with radius r and incremental angle d phi. So the arc length becomes r d phi here. When we join these arc points at theta equal to 0 point, we can draw a very similar to r, radius r, a line indicating radius r here. So let's say this angle is theta, because theta is varying in this direction and it is representing latitude. Phi is representing longitude. Now, if we consider the variation in angle theta as, I represent this here as d theta, this incremental angle d theta, then we get this arc length, which is again similar to this case r d theta. This is r d phi, this arc length is r d theta. Okay, so let's now extend the strip passing through this arc length having uniform arc width. You can see the width of this arc is highest here, it goes on reducing and it becomes 0 here, but this arc length is same whether it is at this point, here, here, or at this point. So this is a uniform width strip and the length of this is r d theta. Now, in order to find the beam area subtended by a sphere, we need to find out the area of this incremental region. And to find this area, we already computed one side of it, which is r d theta. We need to compute the other side, which is this. So looking at this strip width r d phi, we feel it is the same strip which is extending or experienced at this point. So can it be r d phi? No, because the width here is high and it is decreasing as we reach this theta equal to 0 point. So in order to get this length, we need to draw a line here with a right angle here, and since this is theta, this side becomes opposite side. So the opposite side, as you know, is defined as r sine theta. And now you can see, even if we extend this line here, this particular arc length we will get now as r sine theta d phi. I write this once again. It is r sine theta d phi. So this r sine theta d phi and r d theta are the two sides of this incremental region, and in order to find, in a polar two-dimensional coordinate system, in order to find the incremental area dA, we need to take the product of these two sides, which is r d theta into r sine theta d phi, which results into r square sine theta d phi. This term sine theta d phi is called as solid angle subtended by, since we have calculated the area for an incremental region, not for the entire sphere. We have computed it only for an incremental area a small rectangular square, a small rectangular portion, you can say a small square portion on the surface of the sphere. The area dA is represented by r square sine theta d theta d phi. So this term sine theta d theta d phi is called as solid angle d omega. It's not the complete solid angle subtended by the sphere, but it is the solid angle subtended by an incremental area d omega and this r square. So dA is equal to r square d omega. The unit of d omega is steradian or square degrees. Now, what is actually the achievement by finding dA, which is r square d omega, which in turn represents d omega is equal to sine theta d theta d phi. That will be clear once we find the area of a sphere, which is 4 pi r square. Actually, I have given the procedure of finding the area of a sphere in the notes, so you can follow that procedure. But now, from the area, if we assume the radius of the sphere is equal to 1, then a total 4 pi solid angle. This is 4 pi solid angle. It's not a plane angle now. It's 4 pi solid angle subtended by a sphere, and it's represented in, again, steradian or square degrees. So we can represent square degrees as 4 pi square degrees. Now, what is the conversion between steradian and radians? 1 steradian is equal to the solid angle of sphere divided by 4 pi. If we say 1 steradian is 1 radians square, 1 radian, we know it is 180 by pi, it's square, and 180 by pi, radian represented into 180 by pi is always in degrees, so it's square. So 180 divided by pi whole square gives us a number 3282.8062 square degrees. If we approximate this number, then we can say it is 3283 square degrees is what is 1 steradian. So 1 steradian is 3283. Then what will be 4 pi steradian? Because here we obtained that a sphere can subtend totally 4 pi steradians. So in order to calculate that, a simple multiplication, 4 pi steradian is 4 pi into 1 steradian is 3283 square degrees, becomes 41,252.96 square degrees, which can be approximated as 41,253 square degrees. So a sphere which is subtending 4 pi steradian can also subtend 41,253 square degrees. So students, at the end, to understand this concept of beam area, I want to give you a funny analogy. You must have seen a disco ball with many square glass pieces on the surface of the ball, and at the center a light source. In our case, the light source can be assumed as an antenna radiating the field or power. When all the glass pieces. The total number of glass pieces that we have computed on the surface of a sphere is 41,253 square degrees. So if you assume all the glass pieces are glowing due to this light, then we get something like this, a radiation pattern in which equally the power is radiated in all the directions, which is a fictitious antenna known as isotropic radiator. And if we design the antenna such that if it radiates the power in a very small area, focused area, then the beam area reduces. However, this improves the directivity and gain. So the next topic is directivity and gain. See you in the next video. Thank you.